Here is the problem. There is an 80-kilogram shopping cart containing gazelles, which is at rest. There's no friction, and you apply a force of 40 newtons to the cart as it moves a distance of 2.5 meters. Here's what we want to find. First, we will draw an LOL diagram. Then we will determine how much work was done by that force. Then we use a work energy theorem to find the kinetic energy of the cart at the end, and then find how fast the cart will be moving at the end. And we will also solve this problem using kinematics. Okay, so first thing is we will draw the LOL diagram. So inside the O, we will put our system. And the system for this problem is just going to be the cart. And in this problem, everything is happening at the same height. So we don't have to include gravitational potential energy in this problem. So we don't have to put the Earth in our system. Now, with just the cart, the only energy we have is kinetic energy. And the initial kinetic energy is going to be 0 because the cart is at rest. So there's our initial energy bar graph. And final energy, the cart is going to have kinetic energy at the end, but it's not going to be 0 because work was done on the cart. So it was a work that was done which gave the cart kinetic energy. So I'm going to put some work going into the system here. So here's the work that went into the system. And this thing should be about the same size as this. They should be equal areas. So let's calculate the work. So somebody pushed the cart at 40 newtons and it moved 2.5 meters. So look, that's force is 40 newtons, and then we got the displacement, 2.5 meters, and they're in the same direction. So it's positive work. So work is FD cos theta. In this case, theta is 0 because they're in the same direction. So we got 40 times 2.5 times cos of 0 degrees, and this thing is just 1. And so we get 100 joules. So that's the work which was done. So now let's use the work energy theorem. This, by the way, is part A. Work is 100 joules. So the work energy theorem. Oh, sorry. This is part B. The diagram is part A. Let's do part C. Work energy theorem. Initial energy plus the work equals the final energy. Initial energy was 0. So 0 plus work. Final energy is 1/2 mv squared. So this equals 1/2 mv squared. So we can solve this thing for, well, this is, we just say this is kinetic energy final. And this thing is 100, right? That's 100 joules. So kinetic energy final equals 100 joules. So that's the answer to C. Kinetic energy final equals 100 joules. It just equals the work which was done. Now part D, how fast will the cart be moving at the end? So D, we have 1/2 mv squared equals 100, which means v squared equals 2 times 100 over m, which is 200 over 80 kilograms. So that's v squared. So v is square root 200 over 80. What was that? Who can tell me what 200 over 80 is? It's 2.5. Square root 2.5, which is, I think is 1.6 meters per second. So that then is the answer to part D. How would we solve part D using kinematics? First thing you'd have to do is find the acceleration. So force equals mass times acceleration. So acceleration equals force over mass. So the force was 40 newtons. The mass was 80 kilograms. So this is 0.5 meters per second squared. So we got the acceleration. And we know the distance it moved, 2.5 meters. So we would use this equation. V squared equals V0 squared plus 2a x minus x0. Initial velocity was 0 plus 2 times 0.5. Final position was 2.5. Initial position was 0. And that's going to give you 2.5. So again, we get V is square root 2.5, which is 1.6 meters per second. So the same thing works out using kinematics. Are there any questions on this problem?